In this segment, we talk about hyperparameters. They are constants or parameters that may have some influence on the performance and structure of a machine learning algorithm. Hyperparameters are specified when we do the configuration of the code before training the models. Hyperparameters are not the same as model parameters, which are estimated from data or learned from data. Different values or specific choices of hyperparameters could lead to different model performance. Specifically, could lead to different quantifications of metrics for model performance. So knowing exactly which values could maximize the model performance is actually challenging. So what we do is rely on heuristics. Typically, you start with random values, iterate through a few adjustments, and then compare and see which effect the various different values of hyperparameters are having in the performance of the model. This is a process that can be quite long, computationally intensive, and it depends on how many hyperparameters there are. So as you can see here listed, there are a few names of algorithms and models, and the corresponding hyperparameters, k nearest neighbors. You specify the number of neighbors, the metric, the metric. Specifically, this stands here for k, that number of neighbors, right? So that would be a constant that one specifies. That's a hyperparameter. For decision trees, the depth, the maximum depth, the minimum number of samples, the minimum number of samples in the leaf, class weight, criterion, and for the methods that use derivative information, the so-called learning rate. This is also called step size. These are this again is an example of one of these constants that has to be set or fixed at a value. It's not something that is going to be generated by feeding models. And again, kind of like re-emphasizing, hyperparameters and model parameters are two different concepts in machine learning. You can consider hyperparameters as configurations or settings for the machine learning algorithm or machine learning model, while the so-called model parameters are values that loosely embody the rules that the machine learning algorithm seeks to learn from data. So we would set values for the hyperparameters based on heuristics prior to training models. Parameters such as weights are learned or are estimated through the model training. For example, for linear regression, some common hyperparameters are the learning rate for gradient descent methods, the coefficients for regularization, the regularizing penalty term. Those are considered hyperparameters. And model parameters for linear regression models are weights, or also there is another term that's called the bias values. So in this slide, we have three graphs. We have one in the middle, one to the all the way on the left side, and the one to the right. So each of these graphs has several elliptical, it looks like elliptical shapes. They are one located one inside another one. So this is a two-dimensional view of a surface that really is a three-dimensional object, a so-called Cantor plot. The idea here is to achieve a minimum value for that surface, which is right. Just imagine this is kind of like a target. So the three scenarios are scenarios where the so-called small learning rate was set at different values. So for steepest descent algorithms, what we have here on the top, the updates on the weights, they follow a rule where the feature at step iteration n plus 1 is going to use the current values of weights at iteration n, and is going to be subtracted from that current values. There is the gradient, the direction with the information of where, in which direction the values would decrease, would produce the steepest drop. So there is the gradient values, and then there is a coefficient or a scalar or a constant in front of the gradient. That is the so-called learning rate. It's also called the step size. And so this is an illustration of how much the optimization would struggle to converge to the local minimum value. So on the farther left, the learning rate is set to a very small value. In the middle is set to a large value, which causes, so what happens here on the left is that it is converging, but it's taking many iterations to actually achieve the local minimum. In the middle, it's hard to picture here in this two-dimensional, but what is happening is that it's bouncing up and down, up and down, up and down, and it actually has a really, really long time of convergence. It may actually not converge at all. And then the optimal is whenever the alpha hyperparameter was set at a really good value, then the parameter converges in a handful of iterations and in very good convergence rate. In other words, by finding the optimal learning rate or optimal step size, it is possible to reduce the time to train a model. That means that there is a reduction in the computation or compute costs for training the model. So here are just a handful of examples of common machine learning tools or models in machine learning. There are neural networks, there are k-nearest neighbors, there are the decision trees, and there is logistic regression. So each of these models would have a set of hyperparameters. So for example, for k-nearest neighbors, there is the value of k, the distance metric. For neural networks, you can specify the learning rate, hidden layers, activations. For decision trees, there is the depth, there is the minimum samples for lift, class weight. For logistic regression, there is the learning rate and then the penalty coefficient. With all these choices of models and corresponding hyperparameters, one would need to make a decision about how to select the model that yields the best performance with the given data, with the available data.